code authorities will not permit the installation of a 400 amp breaker connected to a 500 kCmil cable that is only rated for 380 amps at its 75 degrees Celsius temperature rating. The fundamental principle here is that the circuit breaker's purpose is to protect the conductor from overcurrent situations. The ampacity of a conductor, in this case the 500 kCmil cable, dictates the maximum current it can safely carry without overheating and potentially causing damage or creating a fire hazard. Using a breaker with a higher ampacity than the conductor's rating defeats this protective function. The National Electrical Code, or NEC, provides specific guidelines on conductor ampacity and overcurrent protection. These guidelines are designed to ensure electrical safety and prevent hazards. In this scenario, the NEC would require the overcurrent protection device, namely the circuit breaker, to be sized appropriately for the conductor's ampacity. Since the 500 kCmil cable is rated for 380 amps, the maximum size breaker that can be used is 380 amps. It is critical to understand the relationship between conductor ampacity, breaker size, and the applicable electrical codes. Firstly, conductor ampacity is determined by factors such as the conductor material, size, insulation type, and the ambient temperature where it is installed. Tables in the NEC, such as Table 310.16, provide ampacity ratings for various conductors based on these factors. Secondly, the overcurrent protection device, usually a circuit breaker or fuse, is intended to protect the conductor from carrying current above its rated ampacity. This prevents overheating, insulation damage, and potential fires. Thirdly, the NEC mandates that the overcurrent protection device be sized no larger than the conductor's ampacity. There are some exceptions to this rule, such as when the conductor ampacity does not correspond to a standard breaker size, but these exceptions are clearly defined in the NEC and must be applied correctly. Ignoring these rules and using a breaker that is too large for the conductor can have serious consequences. If an overcurrent situation occurs, such as a short circuit or overload, the 400 amp breaker will not trip until the current exceeds 400 amps. This means that the 500 kCmil cable, which is only rated for 380 amps, will be subjected to current levels above its safe carrying capacity. The cable will overheat, potentially melting the insulation and creating a fire hazard. In addition to the safety risks, using an incorrectly sized breaker is a code violation. Electrical inspectors will not approve an installation that does not comply with the NEC and other applicable codes. This can result in costly rework and delays in project completion. To ensure code compliance and electrical safety, it is essential to follow these steps. 1. Determine the ampacity of the conductor based on its size, material, insulation type, and installation conditions, referring to the appropriate tables in the NEC. 2. Select an overcurrent protection device, circuit breaker or fuse that is sized no larger than the conductor's ampacity. 3. Ensure that the entire installation complies with all applicable electrical codes and regulations. 4. When in doubt, consult with a qualified electrical engineer or licensed electrician. They can provide guidance on proper conductor sizing, overcurrent protection, and code compliance. In summary, the use of a 400 amp breaker with a 500 kCmil cable rated for only 380 amps is a violation of electrical codes and creates a significant safety hazard. The breaker must be sized appropriately to protect the conductor from overcurrent, preventing overheating and potential fires. Always adhere to the NEC and consult with qualified professionals to ensure electrical safety and code compliance. Let's elaborate more on the nuances of conductor ampacity and overcurrent protection within the framework of the National Electrical Code. The NEC provides a comprehensive set of rules and guidelines intended to ensure safe electrical installations. Understanding these rules is crucial for anyone involved in electrical work, from electricians and engineers to inspectors and homeowners. Conductor ampacity is not a static value. It varies depending on several factors, including the conductor's material, its size, the type of insulation used, the ambient temperature in which the conductor is installed, and the number of current-carrying conductors bundled together. The NEC provides tables such as Table 310.16 and Table 310.17 that list the ampacities of various conductors based on these factors. These tables are essential for determining the appropriate conductor size for a given application. For example, a 500KCMIL copper conductor with THHN insulation installed in a raceway in an ambient temperature of 30 degrees Celsius might have an ampacity of 380 amps, as previously mentioned. However, if the ambient temperature is higher, or if the conductor is bundled with other current-carrying conductors, the ampacity must be derated according to the NEC guidelines. Derating involves reducing the conductor's ampacity to account for the increased heat generated by the higher ambient temperature or the proximity of other conductors. The NEC provides specific derating factors that must be applied in these situations. Overcurrent protection is the practice of protecting electrical conductors and equipment from excessive current flow. Overcurrent can result from various causes, including short circuits, ground faults, and overloads. Short circuits occur when there is an unintended low resistance path between two conductors. This can cause a very high current to flow, potentially damaging equipment and creating a fire hazard. Ground faults occur when a conductor comes into contact with a grounded surface, such as a metal enclosure. This can also cause a high current to flow, posing a shock hazard. Overloads occur when the current in a circuit exceeds its normal operating current. This can be caused by too many devices being connected to the circuit or by a malfunction in one of the devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when an overcurrent condition occurs. Circuit breakers are electromechanical devices that trip and open the circuit when the current exceeds a predetermined level. Fuses are devices that contain a fusible link that melts and opens the circuit when the current exceeds a predetermined level. The NEC requires that all electrical circuits be protected by overcurrent protection devices. The size of the overcurrent protection device must be carefully selected to protect the conductor from overcurrent without causing nuisance tripping. Nuisance tripping occurs when the overcurrent protection device trips unnecessarily, interrupting the power supply to the circuit. The NEC provides specific rules for selecting the appropriate size overcurrent protection device for different types of circuits and equipment. In general, the overcurrent protection device should be sized no larger than the ampacity of the conductor it is protecting. However, there are some exceptions to this rule. For example, the NEC allows the use of the next highest standard overcurrent protection device size if the conductor ampacity does not correspond to a standard overcurrent protection device size. However, this exception is subject to certain limitations and conditions. It is important to understand the NEC requirements for overcurrent protection and to select the appropriate overcurrent protection devices for each circuit. Failure to do so can result in unsafe electrical installations and potential fire hazards. To further clarify the application of these principles, consider a scenario involving a motor circuit. Motor circuits require special considerations for overcurrent protection because motors draw a high inrush current when they start. This inrush current can be several times higher than the motor's normal operating current. If the overcurrent protection device is sized too small, it will trip every time the motor starts. To avoid this problem, the NEC allows the use of overcurrent protection devices that are sized larger than the motor's full load current. However, the overcurrent protection device must still be sized to protect the motor windings from overheating due to overload conditions. The NEC provides specific rules for sizing overcurrent protection devices for motor circuits, taking into account the motor's full load current, service factor, and temperature rise. Another important aspect of overcurrent protection is coordination. Coordination refers to the selective tripping of overcurrent protection devices in a system. The goal of coordination is to ensure that only the overcurrent protection device closest to the fault trips, minimizing the disruption to the rest of the system. For example, in a multi-story building, each floor should have its own overcurrent protection devices. If a fault occurs on one floor, only the overcurrent protection device for that floor should trip, leaving the power onto the other floors. Coordination is achieved by carefully selecting the overcurrent protection devices and setting their trip points. The NEC provides guidance on coordination and requires that electrical systems be designed to achieve proper coordination. In conclusion, conductor ampacity and overcurrent protection are fundamental concepts in electrical safety. The NEC provides a comprehensive set of rules and guidelines for ensuring safe electrical installations. Understanding these rules and applying them correctly is essential for anyone involved in electrical work. Ignoring these rules can result in unsafe electrical installations, potential fire hazards, and code violations. When in doubt, consult with a qualified electrical engineer or licensed electrician to ensure that your electrical installations are safe and compliant with all applicable codes and regulations. It is also important to stay up to date on the latest changes to the NEC. The NEC is updated every 3 years, and it is important to be aware of the latest requirements. You can stay up to date on the NEC by attending training courses, reading industry publications, and consulting with electrical experts. Remember, electrical safety is everyone's responsibility. By understanding and following the NEC guidelines for conductor ampacity and overcurrent protection, you can help to ensure the safety of yourself, your family, and your community. Let's delve even deeper into the practical implications of adhering to these electrical codes, particularly concerning the specific example of a 400 amp breaker and a 500KCMIL cable. Imagine a scenario where an electrical contractor, eager to save costs, decides to install a 400 amp breaker on a circuit wired with a 500KCMIL cable, knowing that the cable is only rated for 380 amps at its 75 degrees Celsius rating. On the surface, this might seem like a minor shortcut, but the consequences can be far-reaching and potentially devastating. Firstly, consider the immediate safety risks. The 500KCMIL cable is designed to safely carry a maximum current of 380 amps. When subjected to a current exceeding this limit, the cable begins to overheat. This overheating can damage the insulation surrounding the conductors, leading to a breakdown of the insulation and the potential for short circuits or ground faults. A short circuit can result in a sudden surge of current, potentially causing an arc flash, an explosive release of energy that can cause severe burns and even death. A ground fault can create a shock hazard, putting anyone who comes into contact with the electrical system at risk. Secondly, consider the long-term reliability of the electrical system. Even if an overcurrent situation does not immediately occur, the continuous operation of the cable near its maximum ampacity can accelerate the degradation of the insulation. This can lead to premature failure of the cable, requiring costly repairs and replacements. Furthermore, the overheating of the cable can damage other components in the electrical system, such as connectors, terminals, and equipment. This can lead to a cascade of failures, disrupting the operation of the entire system. Thirdly, consider the legal and financial implications. As previously mentioned, using an incorrectly sized breaker is a code violation. If an electrical inspector discovers this violation, the contractor will be required to correct the problem, which can involve replacing the breaker, the cable, or both. This can result in significant additional costs and delays in project completion. In addition, if a fire or other electrical incident occurs as a result of the code violation, the contractor could be held liable for damages. This could involve paying for property damage, medical expenses, and even legal fees. The insurance company may refuse to cover the losses if the incident is determined to be caused by a code violation. Therefore, it is always in the best interest of the electrical contractor to adhere to the NEC and other applicable codes. Now let's explore some of the specific situations where this type of code violation might occur. One common scenario is when a contractor is working on a renovation project and is attempting to reuse existing wiring. The existing wiring may be undersized for the new load requirements. Instead of replacing the wiring, the contractor might be tempted to simply install a larger breaker to accommodate the increased load. This is a dangerous practice that should always be avoided. Another scenario is when a contractor is working on a design-build project and is trying to cut costs. The contractor might specify undersized wiring in order to save money on materials. This is a short-sighted approach that can have serious consequences down the road. A responsible contractor will always prioritize safety and code compliance over cost savings. To prevent these types of code violations from occurring, it is essential to have a thorough understanding of the NEC and other applicable codes. Contractors should also invest in proper training for their employees to ensure that they are knowledgeable about electrical safety and code compliance. In addition, contractors should have a quality control program in place to verify that all electrical work is being performed in accordance with the codes. The quality control program should include regular inspections of electrical installations by qualified personnel. Furthermore, it is important to use the correct tools and equipment for the job. Using the wrong tools can damage the wiring and other components, increasing the risk of electrical hazards. For example, when stripping insulation from wires, it is important to use a wire stripper that is designed for the specific size and type of wire being used. Using a knife or other sharp object can nick the conductor, weakening it and making it more susceptible to failure. In summary, the decision to use a 400 amp breaker on a 500 kcmil cable rated for only 380 amps is not just a minor oversight. It is a serious code violation that can have significant safety, reliability, and financial consequences. By understanding the NEC guidelines for conductor ampacity and overcurrent protection, and by adhering to best practices for electrical installation, contractors can help to prevent these types of violations from occurring.